Okay, so let's do Prim's algorithm. Minimum spanning tree. There's 2 of them, right? I forgot the other. Continue without supporting. Wah! Suck it. Upside down E place. Geek for geeks. Okay, I have no problem saying Kruskulls. That's right, Kruskulls. Oh no! Okay, we have discussed Kruskull's algorithm for minimum spanning tree. Like Kruskull's algorithm, Prim's algorithm is also a greedy algorithm. I do like me some greedy algorithms. That's Dijkstra's. Dijkstra's greedy too, right? I only do maximum forest. Yeah, right. You don't know shit about a maximum forest, okay? The second last algorithms course, so the thing is that in the last algorithms course you ever needed, I said that I wouldn't, thank you for that, I wouldn't be able to cover everything. You know what I mean? I wouldn't be able to cover everything that is, I wouldn't be able to cover everything, but I will cover everything that you need. This one's going to be called the last algorithms course you want. I'm going to see if what's it called? I'm going to see if Mark will let me call that, because there's the last algorithms course you need, and then there's the one you want, right? This is the one with a bunch of graph stuff. We're going to talk about strongly connected components. We're just going to do a bunch of graph stuff, okay? Minimum trees, minimum flow, maximum flow. You know what I mean? So this is the one you want, okay? This is not the one you need. This is the one you want. It doesn't cover anything that's like super. It's not like you don't. We did trees. We did tries in the other one. Technically you call them trees. We did trees in the other one. So this one right here? Who just said it? Who said that? What the hell? This man doing stream once every 12 hours. Yeah, effectively right now, because I'm in the process of writing a course. Fully erect, absolutely. Prime. No, I'm just working. Okay, I can't. Where the hell is it? Anyways, trees. Somewhere in here, someone said the word trees. TRIES. Retrieval is what it stands for. So it's called a retrieval tree, right? Or retrieval tree, or shortened for tree. It's a tree. People try to call it a try, but those people, they're not real CSagens, okay? You know what? And whenever someone goes like this, oh, it's a try. I'm like, no, it's not. It's not a try. The guy never said it was a try. The guy specifically said it's a retrieval tree, short tree. And now, was the guy being a dickhead for calling it a tree? Absolutely. But nonetheless, don't rob the man of his agency and his naming, okay? Everyone knows naming is one of the hardest parts of computer science. So guess what? He named it a tree. Tree harder, boys, okay? Where's this gonna be on? Front-end masters. Nah, it's a GIF tree. Okay, cool, GIF tree. Hey, don't look at my code. Okay, anyways, let's keep on going. All right. Let's look at this. Should we start with Kruskulls? We could start with Kruskulls as well. The algorithm starts with an empty spanning tree. The idea is to maintain 2 sets of vertices. The first set contains the vertices already included in the MST, the minimum spanning tree, which is empty because there's no minimum spanning tree yet. And the other set contains the vertices not yet included. So my guess is that if I remember correctly, since this is a greedy algorithm, one can just make a guess right off the rip, right? Oh man, I got to get my drawing pad hooked up. I don't have my drawing pad. Discard. Get the hell out of here. Get him out of here. Get the hell out of here. So my guess is, before even looking at it, it's going to be something like this, right? Let's do some of these. Bam, bam, bam. Right? And let's just say it looks something like this, right? My guess is that it's going to look something like, let's go like this. Let's go 3, 1, 1, 2, right? And so it's gonna look like something like this. You're gonna first choose this one. So then our minimum spanning tree set will be this. Then it'll be this. Then it's gonna be this. Then it'll be this, because it'll be greedy, and this will be 4 versus 5. That's my guess. That's my guess. That's my guess. That's my guess. You know what I mean? All right, at every step, it considers all edges that connect the 2 sets and picks up the minimum weight edge from these edges. Yep. After picking up the edge, it moves the other point, or it moves the other endpoint of the edge to the set containing the minimum spanning trees. So this seems pretty easy. What website is this? This is looks like we're Geeks for Geeks. Okay. You know, this is what we're doing. You guys excited about that? I'm excited about it. Okay. I think I'm correct on that. Let's say a group of edges that connects two sets of vertices in a graph is called cut in graph theory. So at every step of Prim's algorithm, find a cut, pick the minimum weight edge from the cut, and include this vertice in the MST set. The set of the contained, okay. So how does Prim algorithms work? Okay, so here we go. Determine, let's see, an arbitrary vertex as the starting vertex of the MST. Absolutely. Pick the minimum. Follow steps 3 through 5 till there are vertices that are not included in the MST, known as fringe vertices. Okay. Wait, what? Find an edge connecting any tree vertex with the fringe vertex. Okay. This is just a way to say it, I guess. Find the minimum among these edges. Add the chosen edge to the MST if it does not form any cycle. Interesting. Yes. Return the MST and exit. Okay. So that's pretty much what I was saying. I think that's pretty much the same thing, right? Question. Considering my interest in both, we're not talking about that. Sorry. Literally don't understand any of this. Well, we're trying to create a minimum spanning tree. No, not Among Us. That's not what we're doing. MSG is tasty. Course you recommend in TypeScript, Mr. Prime. I love anything on front end masters. All right, there we go. All right, illustration of Prim's algorithm. Okay, consider the following graph here. Okay, so which one? Step 1, first select one. Okay, so we're gonna grab this one. That seems pretty nice. My guess is that we only have 4 and 8 to choose from. So my guess is now you have a second problem with the running time, which is how do you select which edge to cut, right? So they're probably gonna suggest using a heap, because, running time. So this is the problem. Okay, so as you get further into your career, you realize that all data structures are a lie and just use an array. But until then, when it comes to the algorithms, you don't do that, right? And so this is the hard part, is the practical algorithm versus the actual algorithm, right? Or the practical algorithm versus the actual, or the actual algorithm versus the actual algorithm. You get that one? I think you do. A heap is an array. Winky face. You're lucky. You're lucky you're correct. Smartass. I'll let this heap. This flies in the face of my heap, but I'm going to let it happen, okay? He lost it in the war. I lost my heap in the war. Okay, let's see. Okay, blah, blah, blah. So there's really only 2 edges that are available. Yep, that's what I said. Okay, there's only 2. We choose this one, so we choose that one. Boom.
Welcome to Costco.
The edges contain the incomplete MST and to other vertices. So we'd add 2 new edges at this point. We'd add 8 and 11, which means that we'd have to have these interesting weights going on, right? So the minimum weight would be 8, whereas this one would be 12, and this one would be, now, what is that? 4 plus 11, 15. So obviously we choose this one. Now this one's selected. Now we kind of have this problem right here, which is you now have an edge in which is connected to 2 what do they call it? Fringe vertices? Fringe vertices. Okay, cool. All right, step 3, connecting, let's see, the edge connecting the incomplete MST to other vertices. Let's see, among these edges, the minimum weight is 8. Yes, it is. So this one would be the next one. We could have also included 1 and 2. Let's see, 1 to 2. Is this 1 to 2? No, that's 1 to 7. All right. Let's see, the edges that connect the incomplete MST with the fringe vertices are these ones. Okay. So now the real question is selecting these things, right? So I think the interesting part about all of this is how do you efficiently select all of this, right? Exactly. It doesn't show, I know, but we already know that happens internally, right? That's why we're choosing these things. I'll show you a dangling vertice. Oh, baby. Yeah, it doesn't show that. Honest question, what is weight in this context? It's the number associated with an edge. So you can think of it like travel time, right? If this was a map, traveling from 0 to 7 takes 8. Traveling from 0 to 1 takes 4. And so, can you make it so that it takes, what is the easiest way to get to 4? Well, probably on this one is to go 8, 1, 2, 10, right? 8, 1, 2, 10. Yeah. Right? ¿Por qué, Maria? Yes. So, I think that's good. V Hadara. Thank you very much for that brand new Twitch Prime. And Avo Smash for that brand new Twitch Prime. Show back of hand. You know what I mean? You come at me like that, you know what you're going to get, okay? Dijkstra or A-Star? Well, I mean, A-Star is just an iteration on Dijkstra. Dijkstra, okay? Quit being such a Dijkstra, okay? Let's see, the connecting edges. Okay, so I think I understand the algorithm at this point. Blah, 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 blah. The real question is, how do they select which edges they're looking at? Because they're kind of skipping one step that's kind of interesting, which is, how do you know when to remove an edge, right? So this one right here, this yellow one, 11. When do you remove it? Because it just says, okay, find all the edges connecting the incomplete MST to the other vertices. Because if you do that, now you have this whole problem where you actually have... You just keep edging, a lot of public edging. Hell yeah, girl. Because the problem here is that you don't want to cycle through stuff, right? You don't want to go through every single node and check every single edge, right? Because then you're performing an E operation for every single time. So that means minimum the running time would be E, V, but then you have to go through all connected edges, which could be at worst E. So would you have VE squared if you did that? Just saying. But you wouldn't need to do that because you'd use a heap. So then what would you have? What the hell would you have? You'd have like VE log VE? That's way too confusing. I'm off the edge. I'm off the rails here. Okay, let's see the running time. Give me the running time. Shut up. I don't need you. I don't need you. How to implement. Okay, I don't need to implement it. Give me the running time, baby. Okay, other implementations. Okay, the time complexity is... Ooh, why is that? Why is it nodes vertices squared? Okay, if the input graph is represented using an adjacency list, then the complexity of Prim's algorithm can be reduced to E log V. Okay, that makes sense. With the help of a binary tree. A binary heap. A binary. In this implementation, we always consider the spanning tree to start from the root of the graph. Auxiliary space. Okay. Okay, so I have to argue in my head. A binary. I have to argue in my head, why is it V squared? So let's kind of argue this out, right? This is a very important... hey.
And give it to me raw.
Okay, who's giving it?
Spaffy became a member.
Did someone just subscribe to my YouTube? Hey, thank you for whatever you just did. Thank you. It's not a binary tree. Binary heap. 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 I said tree on accident. It's a binary heap, right? Heap. Heap was the answer. I was right on the heap. Heap's probably what you're going to want to use to get the super efficient stuff. But the problem, again, is that you still have this problem with heaps, which is you're still playing... What's a binary heap is just a heap. We typically just call that a heap.
I love you.
Somebody said he catch the live stream instead of video in a video today. So I did. Oh, hey. Well, thank you. Duncan, the dev. Well, welcome. Hey, Prime. Well, hey. O of E equals V squared. Why? How does that make sense? Hold on, help me understand that, because I mean, just like me just trying to look at this. How does edge equal V squared in this situation? Right?
Welcome to Costco. I love you.
For every node is connected, V as V, let's see. If every node is connected, okay. Okay, max connections, okay. Time complexity is vertices squared. Okay, so let's I want to think about this. Why is it vertices squared? Okay, well, obviously you have to visit every vertice. Can we all agree to that one? You have to visit every vertice. Okay, so that is true. So no matter what, it's V minimum. All right, so then you have the heap problem, which insertion and deletion is log the amount of items, log E. So that's where I'm starting to get confused as to where they get where we're getting this v squared business from. So my guess is that this is... How are they getting that? How are they getting that? And also, finally, if v squared... I don't believe you guys. V squared cannot equal e. Because then this statement makes absolutely no sense. Now I'm going to have to go look this up. Is that true? I'm trying to think of why that is true, and I can't think of a reason why that's true. I cannot think of a reason why why v squared equals e. Because then this makes, like, literally no sense. There's no way. No. No, a full graph, e equals 2v, doesn't it? I think you're wrong on this. Yeah, the average number of connections doesn't...
It turns all your bad feelings into good feelings.
All right, hold on. Okay, hold on. Maybe you're right. Okay, so we got 3. Let's do 4. That'd be 1, 2, 3. Let's do 5. Then it'd be... On a fully connected graph, every time you add a node, you do not double the amount of edges. I think you guys are wrong. Okay, I'm gonna go read. I gotta go read. Okay, Radius, thank you. Okay. Radius! 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 Okay, hold on. Okay. My question is about whether big O of v plus e equals this. Basically, if O of v plus e is linear time such that v plus e equals n, wouldn't v squared also be linear time? I assume the worst case upper bound for v plus e is an edge between every vertex. Yes, that would make sense. Which would result in
I love you.
Which would result in v minus 1 squared edges. It's that minus 1 that got me, isn't it? It's that minus 1 that got me. I think you're right now. I also assume that it can consider, let's see. I also assume that it can be considered v squared. So I think it'd be equivalent to this. Any runtime that is a big O of v plus e is also v squared. Let's see, for the reason you articulated. E equals O, let's see, E this. That doesn't mean that it's a good idea to say the runtime is this. Though, since that's less precise bound. In a sparse graph is a much tighter bound than this. Okay, fair. However, the converse isn't true. For example, consider this algorithm. For each node, v and v, for each node u in v, print this. The algorithm has a runtime of this, and its runtime doesn't depend on the number of edges in the graph. Therefore, it would not be correct to say that the runtime is this, since the graph with the... Beautiful. This is actually a really great way to explain it. Okay, there we go. This is actually really, really good. This makes a lot more sense. I like this. Dude, I haven't... So graph theory... Graph stuff I haven't looked at in almost 15 years. Yo, dog, I heard you like a raise. Oh, this makes perfect sense. Okay, so this makes a lot of sense. This makes perfect sense because as you can see right here, so check this out. So start with 3, right? So the equation was this, v minus 1 cubed. Or squared. So, apply the whole FOIL principle, right? You're going to get something like this. V and then some crap, right? And so in big O, you just take this, right? You don't consider all the crap, right? So there is no minus 2V plus 1 or whatever nonsense it is, right? Is that what it is? I haven't foiled since like 7th grade. I can't remember what it is, right? So 2V plus 1. Boom, right? So you just take that. You don't care about this because it's about the growth. It's not about the precision, right? And so you always drop the lower factors. You only keep the highest one, the most beautiful, the fastest growing. And this makes sense. So let's just apply this equation right here. So a fully connected graph would be 3 minus 1 squared, which equals 4, which is, well, that's not correct. Okay, so let's just pretend it's 4 big. Am I missing a -1 somewhere in here? All right, so there you go. Let's try it again. Oh, there's a divided by 2 somewhere in there. Okay, so I must have got something wrong somewhere along the way. Let's see, which will result. Okay, so this statement is incorrect, right? That statement is incorrect because if you look at this, you got 1, 2, 3, 4, 5, 6 edges. You have 6 edges and you have 4. That would be 9 based on that equation. So that's not right either. I'm trying to think of why. Oh, well, this makes a lot. Okay, so that's a much different equation then going on here. Oh, because it's not directed? Oh, well. Oh. 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 Directed, yes. Facts and logic. I just got fact and logic so hard. Trapezoidal sum. Okay, guy. Get out of here, guy, with your trapezoidal business. Okay? Okay, I'm starting to get a bunch of different values here. You got this one. Now we got this one coming in. Okay. Sup? Hey, JD. You like dags? Yo, I heard your dags likes dags. Okay, so I still don't understand why. Okay, so let's try to work out in our head. Why is... By the way, this is a great... For those that are wondering, this is a great way to, like, remember how algorithms work, which is to take a moment and understand... Like, to actually argue with yourself. So instead of just looking at the answer, try to recall it or try to compute it. Why is it v squared? How can we justify this to ourselves? I mean, so the very first simple thing is that every single time we do an operation, we have to visit one node. So minimally, it is v, right? So we accounted for the first v. But the second V, the menage a trois, the big O and the 2 V's, how does this work? This is where it gets confusing. Okay. All right, so this is what I see right away, is that if you consider the binary heap, for every single V, we have to do a log of E, right? So this is the binary heap operation. Every single time we have to do that. That makes sense.
This goes out to the
Do we have to do more than that? Do we have to do more? Okay, so now, hold on. I think I might be... Hey, thank you, the Dr. Webb, gifting out 10 subs. This goes out to the Primogen. That was actual David Hasselhoff. You need to select the next vertex to add to the minimum spanning tree. This operation needs to be done V times. Because they're... Okay, I'm listening to music! Okay, let's hear this one. This operation, which needs to be done V times. Absolutely, correct. Because there are V vertices, yes. So it can take up to V time in the worst case because you must scan all vertices to find the smallest edge. But do you need to scan all vertices? Why do you need to scan all vertices? That's my question. Why do you need to scan all vertices? No, because that should be what the heap is for, right? So the heap... Damn it. Because vert is French for green, and green means go scan them all. Every node is a yeah, that's, you can think of it. Totally agnostic approach is that any possible edge might or might not exist, and since the total number of possible edges grows like this, the expected value for number of edges is this. Okay, now you got me on that one. I'm not exactly following along. All right, so now let's try. Okay, so I'm still having trouble seeing why it's v squared and why it's not v log e. Well, I mean, okay, so actually if you insert E items into a heap, what is the time of that? Is that E log E? It's not really E log E because I don't want to use this yet. All right, fine. We'll use it. Well, priority queue is the heap. That's you're using the same term here. I'm not gonna lie to you. Not gonna lie to you. Hey, hold on. Whoa. What do you mean? Hold on. Inserting n items into a heap can be done in linear time? Where? Link me that. How is that possible? The truth hurts. Please don't lie. The truth is in computer science, Prim knows also Jarnik's algorithm is a greedy algorithm. Okay, we already know all this, okay? Okay, wherever your name is, Prim. The algorithm was developed in 1930 by... Dude, okay, so can we first just take a moment and realize that wasn't the first graph algorithm done in... was it Euler? I always get the two confused. Was it Euler or Gauss that did it? Or they had to do this, like, 7-bridge problem. And they broke it into a graph. Euler, right? Yeah. It's always Euler. Okay, it's always Euler. Gauss is the asshole. Euler is like the cool guy, right? The traveling salesman was Euler. It was God. Got him. Yeah, you pronounce it Euler. I know. No, you don't pronounce it Euler. Euler. I think you actually mentioned it. Yeah, I mentioned this because it's such a fun story. Gauss is GOAT. No, Gauss is a total asshole. He also did a lot of great things, but still, he was a complete asshole. So, Euler. No, Euler. It's Euler. Without heap, should be E log V. Okay. All right, hold on. Let's go look at this one. Okay, description: initialize the tree, choose a vertex, grow the tree by one edge. Let's see, of the edge that connects the tree. Yeah. Not in the tree. Find the minimum weight and let that transfer to the edge. Repeat step 2 until all vertices are in the tree. Okay, that makes sense. Okay, so the reason why I'm tripping up on why is it V squared is because it feels like E is a huge running. It feels like E is the thing you're looking at. Okay. I think I'm starting to see it. I think I'm starting to see it. I'm still struggling why E isn't in there. Okay. I'm still struggling why E is not in there. I think the reason why you'd consider E as a V squared is because that's the worst case given for an arbitrary. Yes. E is definitely more accurate. See, that's okay. So that's what my whole problem is why isn't this thing E? but it feels more than E. And what I mean by that is, okay, so this is what I'm playing in my head right now. So check this out. Let's take the case of a fully connected graph, right? Let's go like that. There we go. We got a fully connected graph, right? All right. And so we start here. Well, what do? We're going to check these three right there, right? 1, 2, 3, right? And so we're going to check a lot of the edges. We're going to pick one of these. It doesn't really matter what it is. After that, we go to this one. We remove this edge from the one that we have. And now we check 1, 2, and then we check the remaining ones, right? And so this feels very E-directed, right? Because, yes, I am visiting. Okay, so I can see this. So I'm definitely starting to see this thing as being something that's going to be like one of those n times n plus 1 businesses or n minus 1 divided by 2 businesses. This is that pattern, right? Because you'll go like this. You'll go to A, you'll go to A, B, you'll go to A, B, C, you'll go to A, B, C, D, right? Right? So I can see the thing happening, right? I can see this thing happening right here.
Welcome to Costco. I love you.
I'm just curious why E is not being used in here. I don't understand
Welcome
that
to
yet.
Costco. I love you.
Let's see. You might want to have one vertex making 5 connections. What? Dylan, stop trying to get me banned. Wait, what is Dylan doing? Dylan, what the hell are you doing? Dylan? Big hell hello notation. Big hell no notation. Hey, Guio, thank you very much. And Flash Kohana. I haven't done graph stuff. Let's see. You're thinking about this wrong. You're not removing edges, just failing to add. You're breaking up the band and reforming without them. No, I was removing it, right? I didn't look at this edge. So once I did this one, okay, so let's call this thing, let's go like this. We're going to call this thing A, B, C, D. And then call this one 1, 2, 3, 4, 5, right? So we start with A, and we actually check A, 1, 2, 3, right? And so 1's been chosen. Then we're actually going to go B, 2, 3, 4, damn it, 6. Okay, and then we go to C. So it doesn't really matter which edge was chosen, 3 or 4. We'll just choose 3 to make it easy. Then we're going to go 2. Let's see, 2. Oh, but then 4 also gets removed as well. Well, it doesn't really get removed because you can't just remove it. Wouldn't it technically get popped from the heap and then you realize this ain't it? You check the edges of the current node. We have to consider if a vertex is visited or not, right? But you still have to you keep a path until it's no longer, let's see, longer than some other path to the same point. Probably possible not to have to traverse every point. I'm also an idiot. Yeah. The problem is that the other algorithms I really know. It's the second time you've done this. Guy. You're going to get banned. Don't. All right, let's ask ChatGPT, because obviously I'm too stupid. I'm not seeing it. I'm clearly not seeing the very obvious thing right here. I don't know why I'm not seeing it. I'm just not seeing it. I must be the dummy. It does take login to extract a node from the queue. Is it a node from the queue? It's not a node from the queue.
Welcome to Costco. I love you.
Hold on. Don't precede it. Explain what is Prim's algorithms running time and why it's that. It never precede ChatGPT. Because the moment you say, explain why it's n squared or some crap, it just might make up an answer, right? You don't want to be doing that. All right. Prim's algorithm is a classic greedy algorithm used in computer science for blah, blah. Okay. I didn't ask that. Notice that I explained what is Prim's algorithm's running time. Did I just get chippitied here? Okay. In terms of running time, the algorithm's efficiency heavily depends on the data structures that are used for the graph and the ordering of the edges by weight. If the graph is stored as an adjacency matrix, a dense graph representation, the running time for Prim's algorithm is v squared, where v is the number of vertices. This is because each extract min operation in the main loop of the algorithm takes v time. All right, this is because, two, if the graph is stored as an adjacency list and a binary heap is used to store the vertices by distance from the current tree, a lighter weight representation suitable for sparse graphs, the running time for Prim's algorithm goes to E log V, where E is the number of edges and V is the number of vertices. I think I get that one. Where E is the number of edges and V is the number of vertices. The extract min operation in this case, log V. Yeah, that's because you have to remove one thing at a time, right? Okay, so you're actually keeping the distances on V.
Welcome to Costco. I love you.
I think I see that one.
Welcome to Costco.
If the graph is stored as an adjacency list in a Fibonacci heap, which, by the way, I cannot do Fibonacci heaps, okay? Those are crazy. Is used to store vertices by distance from the current tree. The running time of Prim's algorithm can be improved to E plus V log V. With the Fibonacci heap, the decrease key operations can be performed in constant amortized time, which is more efficient. Fibonacci heap is straight magic, dude. It is. Like, I've tried, like, I haven't actually really tried to like build a Fibonacci heap, but I've played a little bit. Let's see. For a case of an adjacency matrix, when you're at a given node, you have to iterate over all possible edges in the matrix to find the minimum edge, which is O of V. So O of V squared is to iterate over all nodes in the worst case. Correct. Okay, I can see that. You know, I think actually, dude, okay, I totally understand now why. Okay, I totally get why is V squared equal to E? I'm so stupid. Of course, when you say an adjacency matrix, it's so stupid. How did I not see this immediately? Right? An adjacency matrix is a V by V, right? Where obviously the center doesn't exist, right? Unless there's like self-references, right? And so I'm so stupid for not just making the most obvious connection in my head that E, in worst case, literally equals V squared. It's technically V squared minus V, right? Wouldn't that be like the actual answer? Because assuming there's no self-references, right? Gosh, I'm such a dummy not seeing this. How did I not see this one? How did I not see that? Duh, right? Well, that's so half of that. I mean, first off, half of it, I'm not even convinced that's an easy algorithm to even implement at all. Okay. You can use half the square. Yes, you can use half the square, but that's only in a undirected thing, which we're only dealing with undirected right now. Oh, really? Lightastor. Interesting. Electrical field is voltage squared minus voltage. Are you trying to tell me that there's something oddly similar here, that E sub F equals V squared minus V? If you're dealing with an undirected, then yes, you can only use half. I know, but that doesn't somehow make it... See, nah, this algo is not very intuitive, and Kruskal's and Prims can produce potentially different MSTs depending on the graph if the MSTs are not unique. Yeah. Equals MC squared. Shut the front door. All right. All right, so I want to still understand this one right here. Sorry. This is just me going through college again. I'm sorry. I haven't done Prim's algorithm since 2007. 2007 is when I did Prim's algorithm last. It was a glorious time doing Prim's algorithm. I loved it. I had a great time. Huge fan of Prim's algorithm. Loved it. But nonetheless... They made you do Prims in college? Absolutely. We did Kruskal's and Prims. And so I had to do it by hand on paper and all sorts of stuff. So I'm just trying to remember, trying to regurgitate and relive this is hard. Did you see the new Mission Impossible? No. Tom Cruise is like 9,000 years old. I'm kidding. I haven't seen it. I just don't care. You know what I mean? Is this part? This is what I'm just looking through all the algorithms. I'm just trying to refamiliarize myself with all the graph stuff. You know, when you haven't done a lot of the graph stuff, like I say, in a while, you gotta go back into it. You can't just, you can't just. Dude, that's the stupidest chat I've ever read in my lifetime. I want you to know, I'm not even gonna respect it with an answer. Don't you use graphs at Netflix? What you use at Netflix, what you use in the real world versus this is like very, very, very different, okay? Prim's algorithm, what kind of graph could we use that we could put into memory, right? This wouldn't make any sense. You use more like clustering businesses, right? You don't, and that's like all in machine learning land. You know what I mean? That's why you have to go for Kruskal's for sparse graphs and Primes for dense ones, aka 3 edges max. Lightasor, how old are you? Because you seem like someone fairly fresh off of school to remember these things. Network devices, this makes a lot of sense. Right? I have used I have graph theory PTSD. Okay, so you must have went a little bit deep into graph theory. And I'm in telco. Oh, okay. Okay. This makes sense. This makes sense, yeah. When you're in there, I hope you're doing great. By the way, MSR. Okay, thank you. Fresh off school, aka dweeb. Okay. So let's think about this first one. If the graph is stored in an adjacency matrix, a dense graph representation, the running time for Prim's algorithm is V squared. I guess because I'm still trying to figure out why. Do you really have to check over every single node every single time? Do you have to, like, so for Prim's algorithm, just because maybe I'm doing it wrong in my head. So for this example right here, where pretend we have this right here. I know I'm co-opting my graph right now. So when and it goes A, B, C, D, right? Just like before. When you do that and you check A, then you have to check A, B. Then you have to check A, B, C. Then you have to check A, B, C, D, right? B, C, D, right? Okay. And that's because you can't. Let me just check this in this little representation, because there has to be a point where do you go back over every single node and check every single edge over every single node every single time? Or is there like some sort of updating mechanism that makes more sense? Because that's what I'm trying to think of, is how do you actually accomplish this? Because I'm like, in my head, I'm going over every single node every single time, and that doesn't seem very good. Right? It's a dense representation because you're reserving space for any possible weight between two nodes, even though the typical case, most of those weights will be infinity. Yes. All right, let's watch that animation one more time. Is there a way? Can we just step? All right, so there's 6. Okay, we're I guess that one's 9. Are we calling that one 9? All right, so 1. 1. Okay, so I guess my follow-up question is then, I feel like this thing's kind of skipping something, because how does it know not to check this edge? All right, because it kind of skipped a visited list. Okay, I know, but that a visited list cost, right? Is it a visited list, or is there just an item on that edge? And really, in any sort of way, no, I'm still doing HTMX. I love HTMX. So, even if the flag was on the edge, the running time would be the same, right? You're still just looking at the edge, adding some numbers, or looking at an edge, checking to see if a Boolean is true or false. If it's false, then you add the numbers. Like, in all practical sense, neighbors of visited vertices only. Oh. Wait, hold on. Yeah, edge jokes we're doing. Let's see. Okay. Well, doing the first time when you don't know many edges, let's see, or if v/e, let's see, is less than 2, you end up going through every vertice. However,
Welcome to Costco. I love you.
let's see, has you picking up edge of another vertice due to adjacency while visiting the current vertice. Okay, for some odd reason that didn't help me because either I'm too stupid or I don't get Nako 9999. Yeah, everyone does this. Okay, so why am I missing this? What am I missing here? All right. Let's back it up. Okay. So step 1, we just select a node, right? Node that belongs to the minimum spanning tree is 5. All right, so yep, 9 to 0. Okay, there we go. So then now what do we do? Okay, so in our minimum spanning tree, we start with just the whatever our root node is, right? Is that what we do? Let me just recheck the step-by-step of prims for a second. All right, associate each vertex v of let's just read this one. Okay, the algorithm may informally be described by following the following steps. Initialize a tree with a single vertex. Okay, chosen arbitrarily from the graph. Grow the tree by 1 edge. Of the edges that are connected to the tree to vertices not yet in the tree, find the minimum weight edge and transfer it to the tree. Okay, repeat step 2 until all vertices are in the tree. Okay. I totally get this. It's just I'm trying to get the last part of it. I feel like I could program this. I'm pretty sure I could program it, but I don't think I could program it with the proper running time because I think I would do something wrong.
I love you.
That's what I'm struggling with, is that the algorithm itself seems very simple. It's just how I would do it seems like it would suck, right? Like I would program it in the worst possible way. Hey, the 93 flex, thank you. All right. Associate each vertex Let's say associate each vertex V of the graph, let's see, CV, the cheapest cost of the connection to V, and edge EV, let's see, providing the cheapest connection. To initialize these values, set all values of CV to infinity. Okay, this makes sense. Or to any other number larger than the maximum edge weight. Yep. Set each to a special flag value, indicating that there is no edge connecting V to earlier vertices. Okay, interesting. Okay, so this EV business. Okay, so that's one I didn't see coming. Okay, so I get this. That's our cost thing. That's how we know how to decrement every cost. Right? Initialize an empty forest F and set Q. Ooh, a forest. Damn, we're up in a forest ass at this point. And set a set Q of vertices that have not been included in F. Initially, all the vertices. Okay. Repeat the following steps until Q is empty. Find and remove a vertice V from Q, having the minimum possible cost. Okay. Okay, so this is where having that binary heap is so important. But you need to be able to have a binary heap in which has update, right? Not all binary heaps have update. You have a min heap with update. Yeah. Hell yeah. Hell yeah. Hell yeah. All right. I think that makes sense. All right. Add V to F. Let's see. What is update operation in a heap? Yeah, I know update is just log n. But just to make sure I understand update. Update in a heap is as simple as you go, just pretend this is some part of a tree, right? This is some part of the heap, right? If I update this value, I simply see if this is a minimum heap. Have I become less than this value? Or have I become more than these values? And if I become less, we just swippity swap, and then I repeat the swap operation, right? That's update, right? It goes up. Yeah, in this case, if the value can only become less. Right? If the value can only become less, yes. But I guess in the general sense, you'd have to keep on swapping down or up. Swap the removal with top. Pop the top. Reheapify. No, this is for update. This is you're doing like a little remove, right? Swap, pop, and bop. Yeah, you insert it at the top of the heap. You insert it at the top of the heap and then reheapify. Man, I always forget these things. I feel like I gotta do, yeah, and see how far it can go up. You put it at the end and see how far it can go up. But you still have to fill the hole. So it's not like you can't just, if you remove from the middle, you still have to like heapify from that point. Right? You still have to go upwards. You can't just remove from the middle. It makes no sense. You have to swap from the middle. Update requires the swapping. Right? You definitely have to fill the hole. Wow. You have to swap it. Whenever you insert, you add it to the end and heapify up. When you pop off the top. Is that heapify down? Yeah. Use a dick to fill it? No, dicks are very inefficient to fill the hole. Yeah. So update would be popify and swapify. You don't pop anything in an update. You just update. Right? I graduated, and this is giving me flashbacks. See, I have graduated way too long ago. All right, so the Wikipedia one's actually pretty good. Okay, Wikipedia one's actually pretty good. All right, associate each vertex with the graph. Okay, so I remember this. So we first effectively create something with infinities, right? And then we update this cost with every edge that I have, right? So, you know, if my 1 to 4 becomes, so let's just walk through this one pretty straightforward, because this is actually a really good one. Okay, so this is much nicer. We can visualize the, whatever you call it, much easier here. All right, let's get a new one. Let's just create a very simple graph here. Let's go like this. Your traditional box graph going on here. Look at that box graph. Probably too many to do, but we're going to keep on going. So that means we're going to just select this one, keep it simple, right? So we're going to call this one, 0, 1, 2, 3, 4, 5, 6. I haven't even put in edges. So that means my cost is going to look like this, right? 0, and then infinity pretty much for the rest of them, right? 1, 2, 3, 4, 5, 6. All right, so there we go. I can't do the infinity sign well on a mouse. You get the idea. Edgelord jokes can be funny. Well, they're funny, but when you're doing graphs for too long, edging jokes, they're okay. All right, so there we go. So we got the cost. We have this. I guess I'm just going to probably randomly put some things in here. There we go. Yeah, let's do that. There we go. Classic box me daddy. Now I have to put some weights in there. Okay, so that means if we start here, we would be able to update the weight of 1 effectively and say this was 5, right? So we'd actually be able to just say, okay, this is now officially 5. And then I guess we also have a second one, which is called the set of E to V, which is a special flag value indicating that there is no edge connecting V to earlier vertices. Oh. Oh. Huh. Okay. So we'd also need to have some sort of a... Okay, so that means we also have to have something like your MST list, right? Right, your MST list would have to... What is MST going to have? We have to have an MST in here, right? This is more than anything tells me maybe I need to take your algo course. My first one's all the easy ones, right? Linked list, stacks, breadth first search, depth first search. I even do Dijkstra's. Dijkstra's is pretty easy to argue over it. The VE is a Boolean array to prevent revisiting vertices already, to prevent cycles. Okay, that makes it. That's what I thought it was, which means that that's what I originally was going to do it as, but then it was like a special flag value and I didn't understand it, because then this should be effectively true. And then we have all falses for the rest, right? I think I put in 1 too many.
Welcome to Costco. I love you.
Yeah, that's 1 too many. Yeah, there we go. Does that make sense? The first course was a brilliant refresher for me. Yeah, it's all the ones that you use more practically. Nidens, thank you very much. All right. Unfortunately, I got started super late today, and I want to go be with my wife, and it's 9:15, so I got to be done now. I only get an hour in the evenings to do studying. You know what I mean? I only get an hour. Sorry, I'm stupid. Porque Maria.